In this video, we will discuss the problem merge two sorted arrays without extra space. Previously, this problem has been asked in companies like Microsoft. Let's read the problem statement and see what we have to do in this problem. Problem says that will be given two sorted arrays, that is array A and array B, and the elements are arranged in the non-decreasing order. So we have to merge these two sorted arrays without taking any extra space. So this means that we cannot take any third array to merge these two sorted arrays, and we have to basically modify the existing array A and the array B only. Okay, now what does that mean? So if you will see here, let's take the very first test case. So suppose that you have been given 2, 4, 7 and then 10, and then after that you have been given 2 and 3. So what are the elements that are the smallest element of this array? So yeah, what like now if you see the very first test case here, so we have been given 2, 4, 7, 10, and the second array is 2 and 3. Both the arrays are sorted. If you will see, so what we need to do is we need to arrange or we need to rearrange the elements in these arrays only. So the smallest elements will be in the first array, and we'll keep on updating elements in the second array as well. So you can see here in the first array we'll update 2, then 2, then 3, and then 4. So first array is filled. Now the rest of the elements will be filled in the second array. So 7 and 10 will be filled here. Okay, so this is what will happen. Now let's discuss the second test case as well. Suppose that we have been given the first array A as 1, 5, 9, 10, 15, 20, which is a sorted array. Second array is 2, 3, 8, 1, and 2, 3, 2, 3, 8, and then 13 is given to us. Now what you can see here is that after rearranging the elements, after merging both the array elements, you can observe that we have got 1, 2, 3, 5, 8, and 9 in the first array, and then after that 10, 13, 15, and 20 in the second array. So you can see overall the elements are in the sorted fashion and lesser elements are there in the first array. Then after that rest of the elements follow. So this is what is expected from us. Now how can we solve this particular problem? So for solving this particular problem, we can apply three different approaches. So we'll talk about one brute force approach, then we'll talk about a little better approach, and then we'll also talk about the most optimal approach for solving this particular problem. Now what you can do is, firstly you can apply the brute force approach, that is you can use the concept of insert that is used in the insertion sort algorithm. Okay, so what we can do here is we can start iterating from the last element of the second array. So if you see what is the last, like we'll start iterating from the back side of the second array. So basically we'll start from the last element of the second array and we'll keep on moving in the left direction for the second array. Now at this point when I'll start, so initially I'll be at the last element of the second array and I'll compare it with the last element of the first array. So initially my I pointer will be at the element 13. Okay, and we'll compare it with the last element of the first array. Now what do I observe? I observe that the element of the array, that is bi, okay, it is what? It is basically less than the last element of the A array. It is less than the last element of the A array. If the element bi, if the element of the second array is lesser than the last element of the first array, so this means that this particular element, actually 13, this particular element belongs to the first array. So what I should do is I should basically think of swapping these two elements first. Okay, so it's like you can understand that 20 would come here obviously and 13 will be there. And now after that you need to find correct position for 13 in this particular sorted array, because the rest of the elements are already sorted now. So you need to find the correct position for 13 in the sorted array. So that is why I'm saying that we'll be using the insert functionality of the insertion sort algorithm. So what I did was, initially I started from the last element of the second array. I started from here and I compared it with the last element of the array A. Now since the element of the array B is lesser than the element of the array A, so this means that 20 will come in the second array and 13 will go in the first array. But if 13 will go in the first array, is it at the correct position? No. So we need to use insert function of the insertion sort algorithm to find the correct position for the element 13. Okay, so basically in the worst case, the insertion will take order of n time for a particular element of the array. Okay, now what will happen after that is, what will happen is the element 13 will be at its right place. You can see that 13 will be at its right place. Now after that my index will decrease in the B array, and next time I'll be at which particular element? I'll be at this particular element 8 here. Now I'll again check with the last element of the array. Now why am I checking with the last element of the array? Because if the last element of the array A is greater than the ith element of the P array, Okay, so in such a case, the element of the B array belongs to the first array. Okay, so what will happen is 15 will be expecting that 15 will be going to the second array B and 8 will be going in the first array. So if 8 goes in the first array, again we have to find the correct position at which we should insert this particular element 8 here. Okay, so basically we'll find the correct position at which we should insert this element 8 and it will get inserted. Okay, and then the element 15 will come in the second array. Now after that, my index will be where? Now my index will be at this particular element 3 here in the B array, and I'll again compare it with the last element of the array. Now still the last element of the array A is greater. If the last element of the array A is greater, this means that my element of the B array should go in the first array and 13 should come in the second array. So what will happen is 33 will go here. Once 3 goes here, then the insert concept will be applied, the insert function will be applied, and for 3 we'll find the right position for it in the first array. Okay, now after that what will happen is you can observe that the next element that will be at will be basically 2. Okay, now when we come across this particular element 2 here, so what we are going to do is we are going to compare it with the last element of the array A. We are going to compare it with 10 and we can observe that 10 is greater. So this means that 10 will go to the second array and 2 will be there in the first array, and we'll try to find out the right position to insert this particular element 2 inside the first array. Okay, now after this what will happen is when you will insert, so the first array would look like 1 2 3 5 and 8, and the second array will be 10 13 15 and 20, and this was the expected answer from us. Okay, so you can see that after applying this process, after applying this approach, where we start from the last element of the B array and one by one we keep on iterating for all the elements of the B array, starting from the last element till the very first element of the array B, and we check if the ith element of the B array, if it is lesser compared to the last element of the array A, then the element of the B array, it belongs to the first array. So we will basically transfer that element in the first array and we'll try to find its correct position in the first array, and the last element would come in the B array. Okay, so this will take how much time? If you see for one index, if for one particular ith element of the B array, will take order of n time for finding its correct position in the first array. Because if you see, if I have got 13 here, so 13 needs like if I compare 13 and 20, so 13 is lesser, so 13 needs to be there in the first array. Now for finding its correct position, in the worst case I will take order of n time, and this will happen for every ith element of the B array if I am planning to change the elements, if I am planning to exchange the elements in both the arrays. Okay, so that is why for one element of the array B, I'll take order of n time. So in the worst case, what will happen, since I have got overall n elements with m elements with me in the second array, so I'll take order of m cross n time. So this will be basically quadratic in nature, because we are taking m into n time for solving this particular problem in terms of time complexity. Space complexity taken will be order of 1, because I'll be not declaring any extra array without even if I do it without taking any extra space, still the space complexity is order of 1, but the time complexity is very high because it is m into n. For one element of the B array, I'll be iterating throughout the first array for finding its correct place of insertion. So for m elements, I'll take m into n time. So I hope that this brute force approach is clear. But if you explain it this way in the interview, it will be very useful for you. It will create an impact in the interview. Now after that, what will happen is, if you see the code implementation, so we will do what? We'll start iterating from the last element of the array B, and we'll check if the last element of the array, if it is greater than the ith element of the array B, then we need to do what? Then we want to find the correct position of the ith element of the array B in the A array. And once that is done, then whatever was the actual last element of the array A, we'll update it at the ith index of the B array. And we'll keep on doing this for all the elements of the array B. So that is why the time complexity will be m cross n, space will be order of 1. Now after this, if you will see, can we do it in a better way? Yes, we can do it a little better by applying the concept of swapping and sorting. Now, what do I mean by this? Let's understand this. So basically what we can do is we can ask one I pointer to stand at the last index of the A array, because you can observe that when I was applying the insertion sort approach also, I was always I was always checking with the last element of the array A, because the last element of the array A, if it is very big, it needs to go in the it needs to go in the second array. Okay, because if the highest element of the array, if it is very large, it needs to go in the second array. Correct. And I'll be initially starting at the first element of the array B, because if the first element of the array B suppose that the starting of elements of the array B, if they are smaller, then they need to go in the first array. Correct. So I'll compare. Now when I compare the elements, so let's say this is the jth element here. When I compare these two elements here, so you can clearly observe that the last element of the array A, it is currently greater than the jth element, that is this particular element of the array B. So I'll do what? I'll swap. I have to swap. So what will happen here is now 2 will come here and then 20 will come here. And then what I'll do is I'll decrease my pointer because I have swapped, I have exchanged these elements. I have exchanged the current ith and the jth element which were required to be exchanged. Now after that, let's look at the next element. So we will decrease the I pointer. I will be here. Now j will be increasing. So j will be standing here. Now if you see again, my jth element is what? My jth element is lesser compared to the ith element of the array A. So first array has got higher element. So this higher element needs to go in the second array. So we'll swap again. So when you will swap, what will happen here is 15 is going to come here and then 3 is going to come here. Okay, then after this, what will happen? We'll decrease the I pointer. Now I will be standing at 10 and j will be standing at 8. Now if you observe, so do I need to swap again? Yes, because the element in the array A, it is greater than the element in the array B. So 10 is greater than 8. So this means 10 belongs to the second array, 8 belongs to the first array. So what you need to do is you need to swap again. So what will happen here is 8 will come here and then 10 will come here. Now after that, we decrease the I pointer, okay, and we increase the j pointer. So what happens is now j pointer is standing here. Now, do I need to swap? Because if you see the first element, the first array has got the element 9. The second array has got the element 13. So the first array has got lesser element compared to the second array's element. So that's why it's completely fine. 9 will remain in the first array and 13 will remain in the second array itself. Now after this, you can see that the elements that were required in the first array, they are there. The elements that were required in the second array, they are also there. So but still, there is one issue. The issue is that the elements are not present in the sorted order. So we need to sort these arrays finally. So what will happen here is when you'll apply the sort function in these arrays, so you'll get what? 1, 2, then 3. Then after that, you'll get 5. Then you'll get 8. Then you'll get what? 9 here. Now, after that, you need to sort the second array as well. So when you will sort it, you'll get what? You'll get 10, 13. Then you'll get 15 and 20. And you can see that finally, the first array consists of the elements, and then second array is continuing the legacy of those elements in the increasing order. So this is how we have done it. If you see how much time will the swapping process take, because firstly we were swapping and we started from the last index of the array A and the first index of the array B. So swapping process will take order of n plus m time in the worst case, because we'll be iterating overall throughout all the elements. And another thing is that after that we are swapping the first and the second array. So that would take n log n time plus order of m log m time, because we'll be swapping the first and the second array as well after that. So first thing, because we'll be sorting the first and the second array after that. So the first order of n plus m complexity is because we are swapping. Then after that, we are sorting both the arrays. So respectively, we will take n log n time plus m log m time here. Let's discuss the code for this as well. If you will see here, so what we are going to do is we are going to start from the last element of the array A and the first element of the array B, and then we'll check if we are not going outside. So I should be greater or equal to 0 and j should be less than the length of the second array. If this is so, then we'll check. If the ith element is lesser than the jth element, then there is no problem and we can basically decrease the I pointer. Otherwise, what we will do is if the element of the first array is greater than the element of the second array, then obviously we need to swap and we need to decrease the I index as well as the j index. And after this, the respective elements that were required to be in the first array, they will be in the first array, and the elements which were required to be in the second array, they will remain in the second array. But we need to sort also. Why we need to sort? Because we need to rearrange the order of the elements again. Okay, so that is why finally we are sorting here as well. I hope you have understood this code here and the time and the space complexity for this as well, because space taken will be order of 1 here. Now let's discuss the most optimal approach, that is basically usage of gap method. Okay, so there is a particular sorting algorithm that is known as shell sort. Okay, and in that particular algorithm we use the gap method. So we are taking inspiration of the gap method to solve this problem. I'll tell you the intuition about this as well. Okay, why we take this gap and how it helps us to solve the problem more optimally. Okay, so initially what will happen here is your gap variable will be there. So let me just pull this up a little bit. Okay, so what will happen here is initially we'll the gap. Okay, so we'll declare a gap variable. Now the gap variable will be initially equal to what? If you see here, initially it will be equal to the size of the first array plus second array, uh, divide by 2, and we'll take the seal of that. So what is the size of the first array? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 here. Okay, so the elements are 10, 1, 2, 3, 4, 5, 6, okay, 7, 8, 9, 10. So total elements are 10. You will divide it by 2, you directly get 5. If you got any decimal, then you will have to take the seal here. But we did not found any decimal. That is why we'll have the gap as 5 initially, because the total number of elements were 10 only, so the gap will come out as 5 here. Okay, now after this, if you will observe here, so what we will do is we'll initially start the I pointer from the beginning here. So let's say we'll do some indexing as well. So let's talk about this. We'll initially update the I pointer here, and the J pointer will always start from the gap. It will start gap steps ahead, gap indexes ahead. So where will my gap stand at? Where will my J stand at? So if you see 0, 1, 2, 3, 4, 5. So J will start from here. Okay. Now you can notice this particular thing here, that I'll compare the ith element of the array with the jth element. So since both the elements are in the same array, so I can easily check ai and aj also. So if you will compare here, so what is the scenario? Is the ith element lesser than the jth element? Yes. So things are fine. We'll move both the elements by one index each. So what will happen here is, now you'll observe that my I will be standing here, okay, and my j will be standing here. So we will talk about the implementation, how j will be standing here in the second array. We'll talk about this when we discuss the code also. Now if you observe, so the thing is that the ith element is greater. If the ith element is greater, we need to swap. So swap the elements up. When you swap, what happens? Basically the element 5 will come, since we had earlier which element, so let me just see, we had 5 here. So now 2 will come here and 5 will come here. So 2 will go here and 5 will go here. Now you increase the I and the j index again. So what will happen here is, now the I pointer will be standing where? Now the I pointer will be standing here and the j pointer is standing here. Now again you check. So if you check this pair 9 and 3, so basically 9 is greater than 3, so we should swap. So what will happen after the swap? 3 will come here and 9 will come here. And then you increase the I and the j indexes. Okay, what will happen at this point is, now my I will go here and my j will go here. Okay. So at this point, we observe that 10 is greater than 8. So we'll swap again. So what will happen here is, now 8 will come here. Okay. And then 10 will go here. Now we increase the I and the j indexes. What happens then? Now my I index will be standing here. My j index will be standing here. Now again, 15 is greater than 13. So there's a discrepancy. So we need to swap. Now what will happen here is, 13 will come here and then 15 will come here. Okay. So you can observe that this has happened so far. Now after this, when I'll increase the I index and the j index, so basically you can observe that j will go out of bound. Then we can basically stop, because the right pointer is going outside the array here. Okay, now why did we take such a big gap? Because initially we took the gap as 5. So what happened was, if you will observe all the pairs here, so there are a lot of elements on the left side that are greater than the elements on the right side. Now if I'll check individually, or if I'll do it with a smaller gap, that is, initially we have a habit of taking adjacent elements and comparing. If you compare adjacent elements, you'll be comparing a lot of pairs, and the time taken for a particular element to come at its particular place would be very high. But right now you can observe that, like this element 2 that was there, if I would have done individual comparisons, understand one thing, that 2 was initially 2 was lying in the initially 2 was lying in the second array. If I would have done what, if I would have done individual comparisons, adjacent comparisons, it would have taken a lot of time for me to bring 2 at this particular place. But since I took a very big gap, so what was the advantage that I got? The advantage that I got was that the elements that are not there at the places, the pair of elements that are not there at the places, they will come to their places earlier. The reason being, because otherwise 2 had to wait a lot. If 2 was standing here, if I compare adjacent elements to check whether I have to rearrange or not, that will take a lot of time. But if I compare according to the bigger gap, then I'll be able to easily place the elements relatively closer to their sorted positions, or relatively closer to their expected positions. That will be the advantage that I'm getting here. Because otherwise, if 2 would have been there, I would have had to check a lot of adjacent pairs, and that would have been very tedious for me. Okay. So that would have taken maybe order of n square approach. So right now it is much more optimal for me. Okay, we'll discuss the time complexity ahead when we finally complete this. But you can see that if we take a bigger gap, then the elements which are not there at their places, one by one, they will come to their places by doing lesser number of comparisons. That will be the advantage for me. Okay. Now after that, we'll reduce the gap by 2. Okay. Now if you see the gap value is 5, when you do 5 by 2, you'll get 2.5. So if you're getting 2.5, take it as 3. Okay. So we'll always take the seal value. So now the gap will be what? The gap value will be 3. Now we'll check in the gaps of 3. Okay. So what will happen is, and by decreasing one by one, my gap will eventually come to 1 also. Understand that. So now what will happen is, my I pointer will be standing here. Okay. And my J pointer will be standing 3 steps ahead. So it will be standing at this particular index here. Now, am I okay with this? Yes, I am completely okay. 1 and 3, 1 and 8, I'm okay. Then I comes here and J will be here. I'm okay with this also. Then after that, my I will go here and J will go here. I'm completely okay with this as well. Now after that, my I will go here and my J will be here. Now you observe that the element at the I index is greater. So you need to swap. So what will happen is, now 5 will come here and then 8 will come here. Okay. Now after this, what will happen is my I will be increasing. So it will go at the element 13 and J will be going at the element 9. Now ith element is greater. So swap. Now what happens? 9 will go here and then I guess, let me just check. Okay, 9 will go here and 13 will go there. So yeah, 9 will go here and then 13 will go here. Right. Now after that, what happens? You increase the I pointer. So I pointer is standing here and now J pointer is standing here. Okay. Now is the ith element greater than the jth? Yes, definitely. So what we will do is we'll update. So now what will happen is 10 will be standing here. Okay, let me just check. So yeah, now what will happen here is 10 will be standing here and 20 will be standing here. Okay, then after this, what will happen is when you increase the pointer, I will go here, J will go here, no swapping, and then J reaches the end here. Okay, so you can observe that this is what you have done. Now, after this, when you will divide the gap by 2 again, you will get basically 1.5. So take the seal, you will get basically what? You will get the value as 2 here. So now the gap will be 2. We'll check for the gap of 2 here. Now, what will happen is at this point, my I pointer will be standing here and J will be standing here. So these are fine. Then we check which elements. Then we check 2 and 5 also. They are also fine. Okay, I'll always check the gap of 2. Now 3 and 9 will be checked. So I will be at 3, J will be at 9. Then after that, I guess the elements 5 and 10 will be checked. So they are also fine. Okay, so let me just do this. If you see, so what will happen is I and J are standing here. Now after this, I will be here, J will be here. Still it is fine. Then I will be here, J will be here. Still I think things are completely fine. Okay, then after that, my I will be here, J will be here. Still things are fine. I will be here, J will be here. Okay, so after this, one of the iterations, what will happen here is when the I is standing at element 9 and J is standing at the element 8, I need to swap. I require swapping here. So what will happen is 8 will come here and then 9 would be placed somewhere here. Okay, then we'll increase the I and the J pointer both. So what will happen is I will go here and then J will go here. No need to swap here. Everything is fine. Then after this, what will happen is you can observe that I will be here, J will be here. Okay, so basically this is also fine. Then I will be here, J will be here. This is also fine, and then J reaches the endpoint. So you can see here that there is no issue as of now. Now after this, what will happen? My gap will reduce by half more. Now 2 by 2 will be 1. So the gap is 1. This is the last gap that I want to check. The moment gap is 1, I'll again do the checking, and then after that I'll end my process. So if you see here, and you can see that eventually every element is coming to their place. Now after this, we'll check for the distance of 1, gap of 1. So if you see here, I will be here, J will be here, everything is fine. Then I is here, J is here, everything is fine. I is here, J is here, things are fine. I is here, J is here, things are fine. I is here, J is here, things are fine. But when I is at 10 and J is at 9, things are not fine. So we need to swap. So you can understand that when my I is standing at the element 10, J is standing at the element 9, we need to swap. So we will swap definitely. Now what will happen is 9 will come here, 10 will come here. Okay. And then after that, you can see that all the like other pay, next pay will be what? I will be here, J will be here. Next time what will happen is I and J will proceed. So what will happen is I will be here, J will be standing at this particular place. Okay. Now things are also fine here. But when my I will proceed further, to the element 20 and J will go here. Now I need to swap again. So swap them. What happens is you get 15 here, you get 20 here. Okay, then J reaches the endpoint. And you can see at this point in time, the arrays have got sorted because we have got 1, 2, 3, 5, 8, 9. Let me check the final answer. So you can see we have got 1, 2, 3, 5, 8, 9. Then we have got 10, 13, 15, and 20. That was expected in the output also. Okay, so this is what we have done. Now, why did we took such bigger gaps? Because I told you that if you check adjacent elements, adjacent pairs every time, if you check adjacent pairs, that will be very hectic. That will take n square time or something like that. But that is very big. So what you can do is you can take bigger gap. If you take a bigger gap value initially, okay, and if you take bigger gap value initially, what happens is it helps you to place the elements closer to their sorted positions in lesser number of comparisons. And as you keep on moving, you keep on decreasing the gap so that slowly and steadily you can place every element at their particular position. So this is the advantage of this particular approach here. Okay, if you see, there are two kind of processes that I'm running here. One is basically a gap loop that I'll be running, and always I'll be decreasing the gap variable by 2. So my gap variable will always decrease by 2. Let's look at the code also. If you will see here, initially what we have done is we have taken the length of both the arrays, then the gap is basically n plus m plus 1 divided by 2, because we are taking the ceil here. That is why I am taking, either you can apply the ceil function if it is available in your language, or you can do a plus 1 and then divide by 2 also. That will also give you the ceil value. So basically whenever you will be having decimals, it will elevate one level ahead. Okay, so what will happen is you will iterate till the gap is greater than 0. As I said, your I will start from 0, j will start from the gap. Then after this, we'll be iterating and we'll be placing the elements. Okay, we'll talk about this logic also. And then if after that, every time what you will be doing is you'll be decreasing the gap variable by half, and you'll make sure that you are always taking the ceil value. That is why you're doing gap is equal to gap plus 1 divided by 2, because suppose the gap value is basically 3 here, then the next time gap value expected is what? 3 divided by 2 is basically 1.5. So you expect that the gap value next time should be 2. So if you do 3 plus 1 by 2, you will get basically 2 here directly. Okay, because 4 by 2 will be 2. So that is why we are doing plus 1 divided by 2 here. Okay, now let's understand one more logic here. Why are we not directly swapping? Why are we not checking the ith element and the jth element directly? Why are we applying so much logic here? Because you have to understand one thing very clearly. Suppose, guys, that what happens is, if both, like, see, there are three types of different scenarios that can occur here. What are those three scenarios? The three scenarios that can occur is, basically, suppose that if the I pointer and the j pointer both are lying in the first array. Okay, assume that the first array is having the length as n here, and both the elements are lying in the first array. Okay, suppose that the first array size is n here. This is the first array size that we have taken. You can see a size is n here. Now, if you observe here, if both the pointers are lying in the first array, then we'll compare which and which element. We'll compare basically ai with aj. Okay, so we'll be comparing. If ai is greater than aj, then we need to swap. Correct. So how can we check this? Do we need to apply the concept that I should be less than n, j should be less than n both? No, we can basically check that if the j pointer is less than n, this means that I is on the left side of j only. Correct. So if the j is less than n, this means that both the I and the j pointers are in the first array. So we can basically check the array A elements only. That is, we can check AI and AJ itself. Okay, so that is what we have done here. You can see here that we are iterating until the last here. So you can observe that since both the arrays were there, so J will be basically lastly when J will be equal to n minus n plus m here, then we'll stop. Whenever J reaches the end overall, then we'll be stopping. So this is our stopping condition. And as I said, if J is less than n, basically this means that if J is less than n, this means that J is in the first array. If j is in the first array, this means that I will also be in, or I pointer will also be in the first array. I pointer will also be in the first array. The reason being because, like, if I is on the left side of j only, okay, and if the ith element is greater than the jth, then we will basically swap the elements here. And since the j is less than n, so both are in the first array, so we'll check ai and aj itself. Now, after that, second scenario that can happen is that suppose that one pointer I is standing in the first array and the second pointer j is standing in the second array. So assume a scenario where I is standing here and j is standing here. Now observe this very carefully, what can happen at this point. Okay, it's very important. Now in the original array, if you'll observe, so what is the expected indexing? Let me write that. So if you see here, this is 0, 1, 2, 3, 4, 5, then 6, then 7, then 8, and then 9. This is the original indexing that is expected. Now if you see, my j is sorry, this is the indexing that we are assuming in our mind. So j will be standing here, j will be at 7. Okay, and I will be standing where? Now I will be standing here. Suppose I is standing here. Now what is the size of the first array? The size of the first array is basically given as 1, 2, 3, 4, 5, 6. The size of the first array is 6. So actually this index will be what? If you see here, if my j is greater than, suppose that my I is less than n. If my I pointer lies in the first array and j pointer lies in the second array. So actually according to my logic, my j value will be equal to 7 here. But do I want to check the index 7 in the array B? In the second array, do I want to check the index 7? No, actually I want to check what? I want to check the index that is 1 here. So how can I do that? So if j is lying in the second array, if j is greater than equal to n, if j is greater equal to n and I is less than n, so this means that I pointer is lying in the first array and j pointer is lying in the second array. If j lies in the second array, then you need to check the ith element of the first array with what? You need to check the ith element of the first array basically with the uh, j minus n element of the second array, because if you see, if my j value here is what, 7 here for this particular element here, if it is 7, so 7 minus 6 will give me 1, so that is the actual index of this particular element here, na? So that's how I'm checking it. So let's see the code here. So this is what we are doing here. You can see that we are comparing the like we are checking if I pointer is in the first array and j pointer is in the second array. So if j is greater equal to m, it will be in the second array. Then we check the ai element with the bj minus n element. Okay, and if the element of the first array is greater than the element of the second array, then we swap. Okay, now after that, another scenario can be that if both the elements are lying in the, if both the indexes are lying in the second array. So what can happen in such a case? Let's understand this scenario also. So if you will see here, what will happen according to the logic is, if suppose that I is standing here and j is standing here. Okay, now if both are, basically this will happen when the I value is greater equal to n. When I is in the second array, then j will also be in the second array. Okay, when this happens, so you can observe that the size of the array is 6. Now actually I want to check which particular index. I want to check the indexes, that is index 1 and 2. But actually I'm at the index 7 and 8 according to my hypothetical logic here. Correct. So what should I check here? I should check the b of I minus n with the b of j minus n here. Why? Because if my I value is basically equal to 7 here, so I minus n, that is 7 minus 6 will give me 1. So I will check the index 1 easily. And then after that, when I'll check j minus n, so I'll be able to check 8 minus 2, the 8 minus 6, that will give me 2 here. So that's how I can check that if the left element is greater than the right. Again, you have to apply the swapping logic. So we are applying that. And then as we keep on moving further, we need to increase the I and the j here. So you can observe that this particular while loop that we are having, in the, like, although it is not iterating throughout all the elements, but when the gap will be 1, then obviously you can understand that it might iterate throughout all the elements n plus m. So overall, if you'll see, it is running a lot of times. So the overall movement of the loop will be n plus m times in the worst case, because you can assume that it will be iterating all the like elements here. And if you see the gap loop, this particular loop, so it is running order of log of length times. Let's assume that the length variable that we have here, let's assume that we have the length is equal to what, n plus m here. You can write plus 1 also. So this is the length, total length of both the arrays here. Correct. So the gap variable is basically iterating, and it is always decreasing by 2. Okay, so that is why the outer loop will take how much time? It will take log of n plus m time here. The outer loop is going to take log of n plus m time, because the outer loop is basically doing what? The outer loop is basically iterating and always getting divided by 2, because the variable is getting divided by 2 here. Now the inner loop that we are having, every time, like, you can assume that in the worst case it is running order of n plus m time, because obviously it is iterating. So into n plus m here. So this is the complexity that we have, and the space complexity that we'll have is basically order of 1. So time complexity is order of n plus m into log of n plus m. So basically this is kind of, you can say, something like p log p in nature. Okay, and space is order of 1. This is the most optimal way of doing this particular problem here. I hope that you have understood this approach so far. Let's quickly see the code, how we'll be submitting it. And as I said, this problem has been asked in companies like Microsoft. It has been asked in Synopsys also, and LinkedIn. So I hope you can explain this problem this way. Then your chances of getting selected will be 100%. Okay, so let's see the submission also. Let's try and submit this problem now. So we have written the code. Let's submit this quickly and see if it is getting accepted or not. It should get accepted ideally. So you can see that my code was able to pass all the test cases. I hope you have understood this clearly. Make sure to comment understood. Thank you for watching this video.